will be Monday, maybe Tuesday, because we're almost done with this unit. If you look through these proficiency scales, we've covered it all, we've practiced a whole lot with it, so hopefully we're good. But I will point this out, at least when we have conversations about these things, we don't fully have mastery of our terminology, which means when I ask questions about what type of sequence is this, or what type of function is this, if you don't know that vocabulary, you can't justify well, that does not bode super well. Like, we've got some ideas, we got some procedures, but the concepts we need to develop a little bit more over the next 4 to 5 days that we're preparing for our unit test. With all that said, we have the question up here, what are asymptotes? We're going to cover that today. Over here we have a quick recap on recursive equations. So let's just do this really quickly.
At the table.
So 15, 30. Sure, we'll go with that. Sure. And then hold on.
One of those two things.
is there anything to make sure the camera can see all this? I just thought about that. I don't know if they can.
No, I can. You're good.
They can see it?
Yeah.
Okay. All right. So I'm going to talk about two things really quickly. I'm going to make a quick little task that I hadn't planned on talking about, but I think would be good. First things first, I do want to ask an important question here. Which of these relations is a function? Which of these relations is a function? Is it the table or is it the graph? Could it be both? Could.
Yeah.
So is it both?
Yes.
Okay, why is it both? See, I want to point out what Malia just did is she went back to the definition. We got to know our terminology. What makes a relation a function? Each input maps to one, no, not the same output, to one and only one output. You got to know that, right? So like, if I look at -3, what does -3 map to?
15.
Maps to 15, right? Does it map to anything else?
No.
No. What does -1 map to?
No.
9, does it map to anything else?
No.
No. So like if I look at each input, does it map to only one output?
Yes.
So it's a function, sweet. Okay, second one over here. If my input is 0, can anyone tell what it maps to? I know I didn't write it super big. 3? That's a 2 right there. 0 maps to 2. Does it map to anything else? No. What does 1 map to? 6, okay. So notice, what test could I use, by the way, on that graph that would have helped a whole lot? I can use that vertical line test, right? Vertical line shows an input at a time. It only hits one output, so we're good. We have two functions here. Now, which of these is a geometric sequence? The graph, table. Okay, the graph is an exponential curve, but I didn't ask which one's an exponential curve, I asked which one's the geometric sequence.
The graph.
What did you say? Why do you think it's neither? Is there anything about you? What do you think it is?
I think it is either.
Okay, so Mr. Anderson's thinking neither. Rihanna's thinking maybe neither, but she wasn't confident in that answer. Anybody have an idea why they might be thinking neither?
Well, because I already know one of them.
Which one?
I already know the graph.
What about the graph?
No, the table.
You know about the table? Okay, so why is the table not geometric? Is what?
Adding, so it's eliminated.
So subtracting by 3.
Yeah, but
Okay, so when we go this direction, we're subtracting by 3. Okay, so that couldn't be geometric, right? Does anyone know then why Mr. Anderson is saying that neither are geometric?
They start on the bigger side.
Maybe. Mr. Anderson, can you explain?
Do I have to move the line?
Yes.
Because it's going, it's curving, it's not a straight line.
Well, geometric would be an exponential.
Oh, never mind.
Yeah.
Come on.
P.S. I do want to point out, hey guys, look at that again. I don't have a line on any of these representations. Well, that's not 100% true. Well,
It's not
I
constant.
don't have a line on it.
It's not constant. It's not constant.
It's not constant, it is continuous. Hey guys, I need y'all to remember, if it's a geometric sequence or an arithmetic sequence, it has to be what? Discrete. So guys, this very clearly could be arithmetic. Now, we'll point out, do we know if it's discrete or not? From a table, you can't tell if it's a sequence or not, or if it's a sequence or if it's continuous. But off of this graph, right, that's continuous. That's not a sequence. Now, is it exponential? Yes, and that's, were you going to talk about the exponential curve earlier? Right, Finney said, hey, it's an exponential curve, which means it's exponential, but it's not necessarily a geometric sequence. We got to be careful with our language. See, these are where those terms are wicked important. We got to study the concept. We got to be able to recognize, look at that graph and say, wait, that's not a sequence. It's continuous. It can't be a sequence. You've got to understand those concepts and how they're at play. All right, now, so I talked about functions, I talked about sequences, continuous, exponential. All right, sweet. So here's what I want to do, and I want to point out. Actually, let's talk about recursive here, okay? So what is the way that we like to start recursive every single time?
What?
If I'm trying to write a recursive equation, how would I start that here?
Oh, current.
Current is equal to the previous.
Yeah, minus one.
So you could say the next equals the current, or current equals the previous. So what would I do though? So current is equal to previous. What do I need to do to the previous for this table here?
Subtract.
So if I look here, I'm constantly subtracting 3. So Dalton, I think you asked about the recursive, right? All that we do with the recursive right here is we show the what? What's that minus 3 here?
That's the constant rate of change. No,
Okay,
that's the
constant difference is the name of that rate of change, the constant additive rate of change. But in general, we just show the rate of change. With a recursive, all I'm doing is showing the rate of change. That's it. Okay? I feel like there's something missing though.
What you mean by?
There's something missing. It's exactly what I said. There's something missing from that recursive equation.
Don't we get f x equal to negative 3?
So not, well, I've got the minus 3 right there.
No,
You don't need
it's
it.
not one.
I need what? The starting point. Guys, just saying that we're subtracting by 3 doesn't tell me everything. Like right here, if I do this, let's go with 20, 17, 14, 11, 8, and 5. Am I subtracting 3 here? Yes. Are these the same functions though? Are they the same sequences? No. So is it enough to just have a rate of change? No, we also need a starting point. Guys, when you do a recursive equation, you can't just have the rate of change in there because there's infinitely many sequences and functions that have a minus 3 as the rate of change. We got to have some kind of starting point. You can technically use any starting point, but what's the best starting point that I recommend?
The first one.
The first, so this 15 up here?
Yeah.
I don't know, that's not what I would go with. 0, f of 0 equals 6. Because what type of point is this right here? That's my y-intercept. Remember, that y-intercept is really useful in this equation because what's the explicit equation? Like, what's the explicit equation we like to use with arithmetic / linear? Okay. And what's that b? The slope. The y-intercept. Notice, if I use the y-intercept in my recursive equation, I just get to substitute that into the y-intercept in my explicit equation. What's going to go here for the m? That's my what? That's my rate of change, my slope, which What's gonna be that m in this case?
Negative three.
-3. Guys, if you have a good recursive equation, just put it straight to the explicit. That's what I want us to see here. Remember, what we're doing with this -3 is that we're constantly, repeatedly, which is a type of addition.
Rate of change. Rate of change.
Well, yeah, but constantly adding a -3. Constant added rate of change. And right here we have multiplication, because multiplication is constant, repeated addition. I want us to recognize that. Constantly and repeatedly adding. So Dalton, does that start to answer your question about that recursive? Okay? It's just got to have a rate of change, and it's got to have a starting point. And again, I would recommend that y-intercept because it's right here. Right? It goes straight into that explicit equation. Now, I do want to point out, does anyone see, because this is part of the proficiency scale, we haven't addressed it yet, but it'll help give us a little bit of a preview. Anybody see the x-intercept in that table? Anybody? Going once? -2? Is -2 up here is my x-intercept?
That's what's up. Exactly. Well, it's on the
Feels like
Why are you saying +2? Not the y-intercept, the y,
axis.
not axis, the y value, okay? Hey guys, really quick point of order. If I ask you for the x-intercept, and you're looking at a table and you're not sure, what could you do instead of just staring at it and be like, I have no clue? Could we make a quick graph here to help us see the x-intercept? What is the easiest place to see intercepts? Any guesses? On a graph? There you go. Make sure you label your graph. I'm going to go by 3s to make my life easy. Notice it's -3, 15, -2, 12, -1, 9, 0, 6. Man, look at that beautiful y-intercept. Easy to see on a graph. 1, 3, 2, 0. Look at that beautiful, what is that going to be called? X-intercept. I do want to point this out. On a test, on an assessment, and I'm trying to give you strategies to think here. If I give you a table and I ask you for the x and y intercepts, and you're not sure off of the table, could you make a graph? I need y'all to remember, like, mathematical representations matter. And someone was talking about same outputs earlier. Well, you're referring to the fact that this graph and this table are what? The same. What's that mathematical term, though?
Equivalent.
They're equivalent, aren't they? The same inputs are mapping to the same outputs. When I look at this recursive, are the same inputs mapping to the same outputs? What if I look at this explicit? Will the same inputs map to the same outputs? Yeah. Okay, so we want to recognize the idea of equivalence here. Now, I'm about to pause for a second because here's what I want us to do. So that's a quick recap of like all the things arithmetic sequences. But I want us to look at this graph here. And what I want you to do within your small groups is I want you to try to write an explicit equation for that graph. Okay, so I'm going to make it a little bit bigger. I'm going to make it a little bit bigger in this space over here so that you can clearly see it. But I want you to work within your small groups at your vertical surfaces. Just going to give you all 3 minutes. Take what you know. Think about what you can do to write this equation. So go ahead and go to your vertical surfaces. And I'm going to draw this bigger so that y'all can start to work together. But I need y'all to start talking and thinking. You're writing an equation for this.
Hey, Jay.
Be careful with your language, Dean. You're close, but it's not quite the correct language. What I would point out is you say it's increasing by 3 each time. But okay, see, those are very different things, right?
We're finna write
Because
it.
what is increasing by y? There you go, this right here, added
Katie.
Isn't it 5 minutes?
No.
That one was dry.
I need us to work quickly and efficiently. If I gave 5 minutes, we would ask for 7. What I mean by that is this. If we look at this graph up here, does anyone know the most common mistake or have a guess what the most common mistake that students try to make with finding the rate of change on this graph might be?
Sure.
Nope. Well, worrying about the left side is definitely an issue, but the most common thing I see students do is they go like this. But what is it that they're calculating when they do that?
The difference.
The kind of a difference, but if we're going up 4 to the right 1.
Oh,
That's slope, right? But what does slope only apply to?
Arithmetic.
Arithmetic or starts with an L? Linear, right? We got to recognize that slope only goes with linear. So can I do slope here? No. If you even check the next set of points, notice right here, that's going up 12. Like, is it adding the same amount each time? No, guys, please recognize when we do an exponential, the most common mistake students make is they try to find a slope, but you can't do that. What did y'all end up doing to start us off? Make a table. Now, I know some of us were really worried about the -1 and the -2, but I will point this out. Can you clearly tell what the -1 and -2 map to?
No.
Yes.
No.
You cannot.
No.
So, because here's the thing, and so I want to talk about your numbers in just a second. Right here, what's happening to go from 2 to 6?
It's going up by.
You multiply.
No.
Be careful.
Multiply by
It's
3.
multiplying by. Don't say going up by, because when we say going up, what does that imply? That
Adding.
Adding, right? We're not adding. Notice if you struggled with finding that factor, could you do 2 times my factor?
Yes.
Would equal 6, right? Solve for your factor. The factor is clearly 3. So I do want to point this out. If I'm multiplying by 3 this way, what do I got to do to go backwards? Divide. So that'd be 2 divided by 1, 3. Notice it's not -1, 1. We're kind of assuming that. Okay? You also have -2, 0. And guys, if it was -2, 0, that means I have a what at -2? An x intercept. If I had a -2, 0, like on their table, I'd have an x-intercept. Do we have an x-intercept here?
No.
No, is it close to the x-axis? Yes, because if I divide by 3 again, I'm dividing by another 3. And what's 3 times 3?
No.
2/9. That's kind of close to 0. In fact, it's 0.2 repeating, which is getting closer and closer to 0. We're going to talk about that more today. But so please notice, like, when I get over into this region, I can't clearly tell what it is. So don't worry about it. Can you find your factor just from here?
Yes.
Yeah. Now, I do want to point something out here because I didn't think about this being an issue. And we haven't addressed this before. This idea of a recursive equation only works for sequences. So recursive only works for sequences. We're not going to get into why, because we're not focusing on domain as much, but it ties into the idea of domain. So should we really do a recursive in this case?
No.
No. I just want us to see that. We shouldn't. Don't worry about a recursive here. If it is a continuous function, we're not doing a recursive. Now, 2 things we're going to talk about. We're going to talk about how to just write it from that table, but I do want to remind you, what is the equation of an exponential? There was a formula.
Y equals A times B
Times b.
squared.
No. Why is it not a square?
Because it's not multiplying twice.
It's not only multiplying twice, it's multiplying and then multiplying and then multiplying, and it's changing how many times we multiply, right? So it's a times b to the x. Which, remember, that's why this b is my constant factor, right? That exponent is showing constant repeated multiplication. So times 3 to the x. So what does this a need to be? 2, the y-intercept, right? We're starting at 2, and we're constantly multiplying by 3. That equation works. And how could I check to make sure that equation works?
Plug in.
Substitute some inputs in and get some outputs out, right? Notice if I do that, so if I check 2 2 times 3 to the second, right? My x becomes a 2. What's 3 times 3? 9. 9 times 2 is 18, right? Okay. So that maps to the correct output. Notice in the same vein, if I do -1 here, 2 times 3 to the -1. Anybody remember what a negative exponent tells me to do? It tells me to divide. Guys, we need to remember positive exponents, that constant repeated multiplication, that negative indicates division. Now you can also use a calculator to help you get there, but quite literally that is just 2 divided by 1/3. Or 2 divided by 3. Does that give me the correct input mapping to the correct output?
Yes.
Yeah. Okay, so again, I want to encourage you and I want to remind you, phenomenal job on using an equivalent representation to help you start to write that equation. Exponentials are notoriously difficult for students to write equations from a graph because we try to do slope. Don't do slope. So I'm going to erase this. Don't do slope. But if you make a table, it makes the factor way more clear. All right, do we have any questions from there? We good? Look and see if it looks like we got questions. Okay, so, and then Dalton, you could, if it was a sequence, right, it would have been f of n equals f of n minus 1 times 3, right? So like, that would have been the recursive for that, if it had been a sequence. One word of caution, I do recommend we not use x for our multiplication over here. Why not? Well, I mean, x's and dots can mean multiplication, so why do I recommend not doing the x? Confused with a what? Not with an exponent, a variable. Guys, please don't use that x for your multiplication. It can get confused or misseen as multiplication, or as a variable. All right, really quickly, so if you want to go back to your desk, hopefully that's a little bit of warm-up recap of all the things we've done up to this point. So we're going to continue today with looking at sequences versus continuous functions, just a quick recap, which we did the majority of that already. We're going to talk heavily today about domain and range, and we're going to get into something called exponential growth and decay. Hopefully get past that, we'll see. So your DYU, it may be tomorrow. I say Friday here, but be prepared, it may be tomorrow. But we're going to be focusing on developing tables, graphs, and equations for arithmetic and sequences, geometric sequences, linear functions, and exponential functions. So we are going to create tables, graphs, and equations. That's a big part of this. Which means also, you need to be able to identify the different mathematical representations. You have to be able to say, hey, this is whatever, okay? You have to be able to identify exponential versus linear. You have to identify those things. You need to identify when something would be a sequence versus when it would be continuous, and then domain and range will also be on there. And that will be our last DYU before our test. I don't think I've used my presentation remote yet today. No, where it is. Oh, that's it right here. It's behind me. Okay, so quick notes, right? Unit 2A, proficiency scales, you should have all the foundation in. We should know the different mathematical representations. We should be able to know when we have a relation versus a function. With this intro, I talked about identifying x and y intercepts. Please don't forget, if I give you a table, do you have to use that table to find your x and y intercepts?
No.
No? What can you make? A graph, right? Like make another representation if it's easier for you. But we can identify those using those outputs or inputs of 0. Right now we're going to be focusing a good chunk on domain and range, which we started on that in this class yesterday, right? Domain and range?
Yeah.
Yes, and interval notation, right? Okay. And so this I think is where we ended talking about that domain and range. And so what I want to point out, oh, this is what I ended with yesterday. So first, quick recap. Domain. What do I mean by domain? Set of all inputs, which are also called my
Maximum.
x values. And be careful, right? It's the values for the x. It's not the x-intercept. It is the, or not the x-intercept. It's not the x-axis. The x-axis helps me see the x values. It helps me see the inputs, but it's the x values, okay? And so range.
The set of all outputs.
It's the set of all outputs. Or what are those called? Also called?
X values?
Whatever.
Oh,
Right.
that's what I meant,
Yeah, I got you. Y values, okay? Now, there are a couple different ways to identify domain and range. The set builder notation is something that we're not going to cover because we just don't have the time to focus on it. It's what you have to use. I'm going to hold off on saying that. Let's look. I think we already did this domain yesterday, maybe the domain and range. So this, remember, is the pool situation where we're draining the water from the pool, right? Okay? Now, when we do our domain, what's the first thing that needs to come in the domain?
Negative infinity.
And then what? And then positive infinity. Is that how we would write our domain here?
You put a comma and
Okay, so I need a comma, and I need parentheses. Okay, so I need us to actually break this down again, though, because I think I broke this down yesterday. Is that right, Mr. Anderson?
Yeah.
Okay, and we need to remember something, because I'm going to go ahead and tell you this. I'm not doing negative infinity to infinity on this one.
You doing a minimum.
Okay, so the first value is the minimum input or x, right? The second value is the maximum, okay? So, no, maximum x, because remember, it's just my domain, okay? So if we look at this graph, when we think about draining a pool in the time that has gone by, can I go to negative infinity in terms of time? No? So what is the minimum x value? Isn't this my x values right here? 0, 1, 2, 3, and so what is the x value? As Malia was saying? The x value there is 0, isn't it? When we say x, we're talking about left and right. The furthest this goes to the left is that x value of 0. So what needs to go here? 0. The minimum x this time is not negative infinity. It's 0. Okay? Now it's a comma. What's the maximum x?
4.
Well, notice, and so I guess it's unclear here, there's an arrow there.
Positive.
So it does keep going, technically, okay? So, but there's a little bit of a trick to this one, because let's be real, if we're talking about draining a pool, is it going to take forever?
Yes.
No.
There is going to be a stopping point. It's hard to really see it with exponential. So, because there's an arrow, I'm basing it on the graph, so like, it's important to understand what the function says versus what the real world says. In this term of this function, does it keep going to the right?
Yes.
Yeah, okay, so it's going to go to infinity.
0 get a bracket.
Okay, why does the 0 get a bracket? I would say, not just because it's a whole number, because, okay, so because, I'm not going to get too super technical on it, and I'm not going to hold y'all super accountable on this. I'll be nice about it. But if this had been an open point, right, so ignore the colored in, if it was an open point, does the graph actually get to that 0?
No.
No, remember, if it's an open point, we don't actually get there. Okay? So if we don't actually get there, we wouldn't use a bracket, we would use a parenthesis. Okay? Huh?
I thought we used parentheses for range.
Well, we use parentheses in general for infinity because can you get to infinity?
No, it keeps going.
It just keeps going, so can you ever actually get to an infinity?
No.
No, so remember when I said if it was an open circle, we would use a parenthesis here, and
Oh, okay, I know.
because we wouldn't actually get there. Why do we use a parenthesis on this infinity? Because we don't actually get there, okay? So if it doesn't actually equal it, then we have to use a parenthesis. And I know some of y'all listening and they're like, parentheses. So if you're talking about both, it's parentheses, because parentheses is plural. Parenthesis is singular, it comes from a Latin root.
So when it's open, it's a bracket.
No. When it is closed, it's a bracket. So like if it gets to that, yeah, if it was open, if you can't actually get there, it's a parenthesis, okay? So again, just in general, if you cannot get there, it's a parenthesis, okay? So if you cannot get there, it's a parenthesis. If you can get there, if that value is actually ever equaled, then use a bracket, okay? You don't need to go to vertical surfaces. I'm gonna give you all a minute or two to think through what you think the range for this will be, and then we have a short little exploration to make a little bit more sense out of it. So please write, just talk to your group, come up with an idea of what you think the range for this might be.
I think the range would be. So I'm gonna say, so it's closed, so obviously we use parentheses.
Let me ask you a question. Can you ever get to an infinity? So we use a parenthesis when we can't get there. If it's a closed point, can you get there? Does the function ever equal that value? So if the function equals that value, you're not using a parenthesis, you're using a bracket. Okay? So think about it. Think about what we have up here. As you can see, what do y'all think? Talk about it at all? Place the graphs right there, right? We're just basing off of, like, if we're doing range, what's going to have to come first?
I got it.
What's the first number?
Okay, well, look back at your domain. What came first in the domain? Which x value?
Which one, like x-axis or
No, it's not.
Laser.
The range is 0.
Because remember, they're both x
What's the
values.
range?
What came first?
I think we're doing the left one. Ain't we doing the left one?
No, we're doing the one on the right. There's a minimum x, right? The minimum has to come first. So when you're doing the range,
Is it the clock on your thing?
well, that was for the domain, right? Because it was the minimum x to the maximum x. Remember, I'm asking you to think about the range now. Domain was minimum x to maximum x. What's the range going to
Maximum one.
be? Say again.
Maximum one.
Okay, maybe. Think about that. But I mean, range is something about y's, right? So that's at least going to get you started.
Range is.
What do we think?
Huh?
So what are y'all thinking?
Like the close out there,
0 to 1500.
I
All right. Hopefully we have at least some ideas. We don't have to have it perfect or not. Aces, what are y'all thinking about? What did y'all come up
We
with?
put 18.
Huh?
We got 18.
You got a single number for the range?
Yeah. Oh. I didn't get that far for the second one.
Say again.
I didn't get that far for the second one.
Okay, why are we talking to Jacob then and not our group of
I
us?
was trying to see like.
Kings, what were y'all thinking about then?
Oh, no.
You didn't have anything?
think about 18 and 6.
18 and
Don't ask
6.
me why.
Where is on your 18?
Yeah, where's the 18 coming from?
Oh,
18,
yeah,
yeah.
give me the example on that you wrote.
Oh,
My bad.
no, this one right here.
18.
The one we just did domain. You should have a copy of the graph in your notes from yesterday.
Still on.
Okay, so what about over here? Did y'all talk about anything? 0? So 0 is the range, the whole range?
Oh, wait, but the highest one was 675.
I can't see the high one.
Okay, I'm gonna hold on to that. Okay, so Jax, what were y'all saying though? When I came by and saw the deal?
0 to 1500.
So I see why you're thinking 1475, because that's the highest we see on the x-axis right here. But remember, there was another point up here at what y value? 1500. Remember, at 0 minutes, how many gallons of water were there? 1500. Okay, so that sounds like a good start. But there's a couple of things we need to think about with this. So be careful, because this 0 right here is not the same as this 0. Because what is this 0?
0.
It's the minimum x. I need y'all to be careful with that attention to details. That's the minimum x right there. What is this 0? The minimum y. So, really quickly, because when I was talking with y'all were thinking maximum to minimum, right? Hey guys, I need y'all to hear me clearly on this. It doesn't matter what you're talking about. If you're using an interval notation, you always go from a minimum to a maximum. The difference with range is it's the ones. So guys, it doesn't matter whether you're talking about domain, range, intervals of increase, intervals of decrease, which we haven't studied yet, but if you are using an interval notation, what always comes first? The minimum. What always comes second? The maximum. Always start at the minimum. Notice, this group said 0, which I'll point out there's an arrow here, and it keeps going down. So I'm curious why they said 0. We're going to explore it more later. Okay? But they said 0. Do y'all think we put a bracket or a parenthesis on this?
Bracket.
Bracket. So I heard one person say parenthesis, but the majority is thinking bracket for now. So let's go with that. What about that 1500? So by the way, notice they're saying the minimum y value is 0, and then the maximum y value is 1500. Bracket or parenthesis? Bracket.
You can't go past.
Can't go past that 1500. That's where it stops, right? It stops at that 1500. Now, here's what we're about to do to make a little bit more sense out of it. So I'm going to come back to this in a second. Oh, it does.
Big setup.
Well, no, I put a... I don't know where I put it.
You got a problem?
Make the table up there.
Oh, I put it in the wrong spot. Found it.
I don't know.
I don't know how I put it in the wrong spot. Okay, so one person per group. I need you to go grab calculators for your group.
He's right there.
What's up?
Oh, Jaheim, go get our calculator.
By the way, sorry, let me also clarify. I should have said this better. Only one calculator per group.
Y'all don't do this.
That's my bad. One calculator per group. Okay, so you do not need multiple calculators per group.
We got one.
Okay? So right here, okay, we're going to come back to this later, okay? So the groups that are going to come up to here, do not erase this. I'm going to erase everything else. But what we need to learn is a new detail that we have not talked about yet. And we're going to learn about something called a growth factor, a decay factor, and a horizontal asymptote. A growth factor, a decay factor, and a horizontal asymptote. Okay? So that's what we're about to learn. Here's what I need you to do if you have the calculator in hand. I need you to go to, turn it on, go to the home button. So you should be looking at this screen, not menu, home, okay? So I need you to pull up the calculator. I need you to go to number 2, browse. Okay, so number 2, browse. You should be able to go, I believe, to My Documents. Click on My Documents. No, that's all My Documents. Hold on. Where did everything go? Okay, so, yes, so you need to go to transfers 91725. There's a file that says transfers 91725. There it is. Nope, it escaped. That's not the right one. Oh. No, there you go. Transfers 91725. It should say exploring, I don't know, what was the title of that? Exploring exponential functions, or exponential functions exploration, okay? So, do not save your old document.
What'd you say it was?
That one right there, hit enter. Do not save the old document, just open up that exploration.
It's not working.
I promise you it is.
It's open.
We're supposed to get a graph.
Yep, you should have a graph. Okay?
It's not working.
Now it's working.
No, it's exponential. Something.
Okay? It's supposed to be exponential. It's exploring exponential function,
Base.
or it's exponential functions exploration.
It's
Okay.
an exponential function. Base x something.
Yeah. All right. So So this is what you should be looking at right here, b raised to the x. Please notice, right? And so I'm just going to set this up a little bit. So what I have is f of x equals b raised to the x. What is my b currently? 0.6. Okay. B is my 0.6. It should be the same on your calculator, I believe. Okay. So right now that function is 0.6 to the x. Okay. So here's the directions I need you to follow and listen closely to. Right now, is this function decreasing or increasing?
Decreasing.
We're good with the fact that that's decreasing. It's going down, right? So with exponential, we're going to call that an exponential decay. Okay? Mr. Anderson, can you click on the arrow to the right? So notice there's little arrows down here. All right? Mr. Anderson's going to click. Keep going. Until I tell you to stop. Keep going. Okay? Keep going. All right, there you go. So now notice, what do we have here? Is it decreasing again?
Yeah. Well, no,
It's increasing. Guys, if we go left to right, is it going up or down? It's going up, right? So that's increasing. And I'm not going to call that an exponential decay. I'm going to call that an exponential growth. Remember on that proficiency scale? So guys, there's lots of ways we could describe it, but if you remember on that proficiency scale, I think I talked about a decay factor and a growth factor. Okay, so exponential growth and decay. So here's what I need you to do in your small groups. I need your responses on the vertical surface. One, I need you to figure out what type of base creates exponential decay. I need you to do the same thing for exponential, I should say decay. Exponential what? Growth. Okay? And the final thing is, nope, not solving anything. What base does not work? Let's say it this way. What base doesn't work for exponential functions? So guys, Mr. Anderson and I can help you go around, but all you're going to do is you're going to click these arrows, and those arrows are going to change your base. And so what I want you to think through and try to find is what bases will create an exponential growth, what bases will create an exponential decay, and finally, what bases will never work for an exponential. So all you have to do is write responses to those three questions on your vertical surface. 3, 2, 1, go! Do it live over here? So please do not sit. I need more of us actively engaged in this conversation. Now I'll point this out. A lot of you, yeah I know, right? Like, why do I talk? A lot of y'all saw the pattern that I wanted us to mostly see. So first things first, let's actually start with number 3. Let's start with that. So what base does not work? So what was the first base a lot of y'all noticed?
1.
So base cannot equal 1. Notice if the base here is 1, Victoria, I know I talked about it with your group. What do we call this function when the base is equal to 1?
Continuous.
Yes, it's continuous. It's another C word though.
Constant.
It's constant. Remember, if I look right here, what is the y value for every point here? 1. Notice that's not a constant rate of change. It's a constant function because it stays the same. Okay? So there is a difference. Hey guys, I understand there's cool stuff outside, but I'm also trying to teach you cool math. Okay. It's a constant function because the y value stays the same. So the base cannot equal 1. All right? What's another base that it cannot equal?
Negative.
Okay, so before even the negatives.
0.
0. So Mr. Anderson, can you go to a base of 0? Base of 0.
No.
Is that an exponential function?
No.
No. So the base cannot equal 1. The base cannot equal 0. Because I want you to think about this. If that base is 0, what are you repeatedly multiplying by? 0. It's staying the same, right? Like, that's not helpful, okay? So the base cannot equal 0. And I heard someone say negatives, right? Yeah, what happens when that base becomes negatives? It's not a what? It's not a function. I need us to recognize that. So I want to point this out. Notice how for each of these it was an equal to, and then what did I put through that equal to sign? A slash. What does that slash through it mean?
It's not equal.
Not equal to. B cannot equal 1. B cannot equal 0. Now, how would I indicate all these numbers to the left of 0?
Negative?
They are negative, but I'm sorry. What symbol can I use to indicate everything to the left of 0?
Slash is
Slash.
the way, I don't know.
Not yet. Listen. What inequality symbol can I use to indicate everything to the left of 0?
Less
Greater
than?
than 0.
Less than, greater than, what?
Well, which one is it? Is it
Less
less than or
Less
is
than.
B less than 0 or is B greater than 0?
Less than.
It's less than.
If I'm going to the left, it is less than. Okay?
Yeah.
But can B be less than 0?
Yeah.
No. Remember, we just said we can't have what kind of numbers? Negatives. B cannot be less than 0. It cannot be negative. That's what this is saying. By the way, I have a Freer model for y'all to take notes on, so don't write this down yet. So it can't be negative. Now, let's get to what it can be. Let's talk about our exponential growth. This one I think was a little bit easier for a lot of us. So exponential growth. Over 1 was a common language. Over there y'all said anything above 1, right? Okay, so what's a way using these idea of symbols here that I could indicate that it is above 1? B is greater than 1. Okay? And I want to point this out. I talked to one group because what they were originally saying was, okay, 1.1 and above. Okay? Which, let's think about this for a second. If I take 1,000 and I multiply it by 1.1, I'm going to get 1,100. Is that growing? Yeah, okay. But I need eyes on this too. If I take 1,000 and I multiply it by 1.01, does anyone know what I'm going to get this time?
1,000.
1,010. Did that also grow? It was less, but it still grew, right? So if I take 1,000 and I multiply it by 1.001, what do I get?
1,001.
1,001 is very, very small, but did it still grow? So it's not just the 1.1 and above. If your base is greater than 1, it is going to grow. And that is going to be called a growth factor. Okay? So whatever that base is, that's going to be your growth factor. All right, next piece. It was the exponential what? Right here.
Decay.
Exponential decay. Now I think this is where a lot of us were having the most trouble. So I want to talk about this detail. A lot of us realize that the base has to be less than 1. Alright? A lot of us said, hey, the b has to be less than 1, but I need y'all's eyes on this to pay attention. 0 is less than 1, isn't it?
Yes.
Yes? Negatives are less than 1, aren't they? Yeah? So is the base just anything less than 1?
No.
No. It can't be 0 and it can't be a negative. So what does this base have to be in between? I think, no, where did I see it? Yes. Okay. This is kind of what we saw over here, but this is a little bit better language. If the base is between what two numbers? 0 and 1. Okay, so Rihanna, this is what I was trying to get you to on the inequality, and I apologize I didn't get that
That's what I
clearly.
was trying to say when I had 0 and 1.
But that's why I said like you need to use better language with it, or there's a symbol way to do it in a second. But you have to say it's between 0 and 1. If you just say 0-1, that means it could be 0 and it could be 1, but we can't be either of those.
That's what I meant.
Okay? So what do I need to put here to indicate that my base is between 0 and 1? We need a 0, right? What needs to be between the 0 and the base to indicate that this base is between 0 and 1?
Greater than.
Not a greater than. So what this is saying is that 0 is less than the base, which means the base is greater than 0. And the base is less than 1. Notice literally, what is that base in between? It is between 0 and 1. So it's an exponential decay. It's a decay factor when the base is between 0 and 1. Okay? Mr. Anderson, where did you put? Oh, they're right here. Okay. Okay, so what I need y'all to put on this sheet, we'll fill more of this out later, but I need you to fill out the little quadrant that says base of exponential functions. Right. I would not just write out what bases you can and cannot have, I would fully write out, maybe show a sketch of a graph with those different bases in there next to it, right? So I would say, hey, in an exponential function, base cannot equal 1, base cannot equal 0, thank you. Oh yeah, because you already had one. And b cannot be less than 0. Write those explanations with it. With the exponential growth, show what the base has to be, but then show a quick sketch of why it's growing. What happens when you multiply by a number bigger than 1? After you take some notes. Okay? So guys, top right quadrant on the exponential side, I need you to write about exponential bases, or bases of exponential functions. Bases of exponential functions.
And where I'm putting, because I don't understand none you're talking about.
Well, Rihanna, you hid your face while I was explaining it.
Yeah, because I'm getting irritated.
Well, I'm trying to break it down so that you can understand it. Okay. So I want to talk about one more thing with these functions that we need to recognize, okay? When I look at this function here, right, and I'm playing around with this exponential, looking at that base, we need to recognize this exponential curve, and we need to recognize on this side it's growing. Well, really it's decaying because it's moving left to right, but these are super positive values up here, right? But what's happening through here?
It's decaying.
It's decaying, but like, what's happening along in here?
Oh, okay. Nothing? It's just staying the same?
It's becoming what? So
It's
we're,
staying the same, so, yeah.
sorry, hold on. Brianna, I need y'all to hear this because this is something that is typically difficult that I want us to clearly understand. I'm going to break it down really heavily, but I need us engaged in this conversation. So Chelsea, what were you saying? What's happening here?
It's constant.
It is, well, oh, so you're saying it's staying the same?
Yeah.
Okay. Malia, what were you going to say here? Okay, so we're thinking it's constant through here, right? But I need us to pay attention. Like, what type of function is this again?
Exponential.
It's exponential, which means it is constantly doing something.
Somebody, he coming. It's constantly decaying. What?
It's constantly decaying, but it's constantly what? Multiplying. When we say it's constantly decaying, that means it is constantly multiplying, right? Hey guys, y'all need to pay attention to this. So, when I am looking at x equals 2, that's 1/2 being multiplied how many times? Twice, okay? Does anyone know what 1/2 squared is?
2.
2/2.
So remember, it'd be 1 times 1, which is?
2. 2 4?
Yo, 1 times 1. 1. 2 times 2 is? 4. 4. Okay, we see that 1/4 in there? It's a pretty small number. But let's go to an x value of 3. That's 1/2 to the third, which is, yeah, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So 0.25, 0.125. Okay, when I go to the next x value, what am I going to do again? I'm going to multiply by what? Well, it's going to be to the 4th power, but what does that mean I'm multiplying by? It means I'm multiplying by 1/2 again. Which means I need us to pay attention. Listen, guys, what are we constantly doing? We're taking a positive number and multiplying it by another positive number. Okay? If I keep multiplying by a positive number, what kind of number am I going to have?
A positive, I guess? Wait, what you?
If I keep taking a positive number and multiplying by a positive, what am I going to get?
A
A
positive?
positive times a positive is a...
Positive?
Guys, it's not negative, it's positive, please. We got to know, a positive times a positive is a...
Positive.
I'm about to lose my mind if someone else says negative after I just said it's positive, and everyone else is saying positive.
Negative times positive is negative.
Correct, thank you. The only way to get negative is take a negative and multiply by a positive. Right here. Positive times positive is
Positive.
And I heard someone earlier say it's going to get to 0. But I need you to look at this again. We just said a positive times a positive is
A positive.
positive. So it's going to stay what?
Positive.
It's going to stay positive. Is it going to get really close to 0?
Yes.
Yes, but it's getting half every time. Half every time. Half every time. So is it actually going to get to this 0?
No.
No. I need us to recognize that the function approaches 0, but it doesn't get there. I need you to recognize this. I want to show some notation here. But I need us to understand. Like, we keep multiplying by a positive, and I multiply by a positive, multiply by a positive, multiply by a positive. It's going to stay positive.
Yeah.
So does it ever get to 0?
No.
The answer is no. Okay? So, earlier, when we did range earlier with that exponential, does it actually get to that 0? Notice what we just said is it approaches 0. Does it get there though? No. So do I need a bracket? No. We don't get to the 0, guys. No, it definitely won't. Remember, that's what we just talked about, Walter. If I keep multiplying by a positive, what's it going to stay? It's going to be a positive. If I take 1/2 to the 100th, I'm multiplying by, no, please don't do that. If I multiply by 1/2 to the 100th, or I multiply 1/2 100 times, what kind of number do I still have? It's still going to be positive, guys. It doesn't matter how many times you multiply by a positive. It doesn't matter how many, it will get close to 0, but it is going to stay positive. So the function only approaches 0, but doesn't get there. Does anybody know what we're going to call that line that we're approaching but don't get to? Horizontal asymptote. There's a line right here. Is that function getting close to that line?
Yep.
Does it get there?
No.
Nope. An asymptote and I will say this, I'm only going to call it a line for right now, but technically it can be a curve. An asymptote is a line that a function approaches at some infinity. I think there's a quadrant dedicated to horizontal asymptote. Okay? An asymptote is a line that a function approaches at some infinity.
What?
The very first year that I ever taught, I had my mind absolutely blown by a professor at UA named Dr. Gleason, where he pointed out in the kindest ways that my understanding of an asymptote was way wrong. And it wasn't just me, it is a whole lot of mathematicians and math teachers that misunderstand asymptote because we don't think about it like this. This is what an asymptote is. It is a line, technically it can be a curve, that a function approaches at some infinity. Notice, this isn't, it's approaching it and getting closer and closer and closer to it the further we go. And what is my x going towards way over here? What's this x going towards? Infinity. But what's my y going towards? What's it approaching? 0. So notice that this infinity, way over here, the function approaches 0. Now, that's just an asymptote. Any guesses why we call it a horizontal asymptote? So the x-axis is what kind of line? Horizontal line. It is called a horizontal asymptote because it is a horizontal line that is the asymptote. You know what every exponential function has? An asymptote, not just any old asymptote, horizontal asymptote. So I'm going to have to bring this information over here, but I need us to pay attention to this. Hey guys, we need to have this note under horizontal or under asymptotes. Exponential functions have what kind of asymptotes?
Horizontal.
Horizontal asymptotes, because one, notice, is it both ends that are approaching the horizontal asymptote?
No.
No, it's only one end. So because one end will approach a horizontal line at, I'm going to go ahead and show you this notation. So, Mr. Anderson, can you go to a base of 2? Yeah, a base of 2. Okay. I'm sure it's like some stupid decimal e to the negative something. Okay, here's what I need us to finish on, and I need us to recognize. So I'm going to talk about what the horizontal asymptote is. Can you give me like 2 minutes? Okay. Here's what I need us to recognize about this horizontal asymptote right here. Notice now, Mr. Anderson got us to 2 to the x. Notice if we go into the negatives, what does a negative exponent tell me to do? To divide. Notice what is, if I take 1 and I divide it by 2 100 times, what are we going to get close to? 0, right? Notice how my horizontal asymptote is this way. Notice this is, what is that y value approaching again? Y is approaching 0, so do you know what my horizontal asymptote is going to be? What's y approaching? 0, so y equals 0 is my horizontal asymptote. Oh, I should probably talk about this notation over here, sorry. Guys, this arrow right here, anyone know what that arrow means? Kind of approaches. This arrow means approaches. So what I am saying over here is, in a shorthand, a mathematical shorthand, one end will approach a horizontal line at x approaching either positive infinity or at x approaching negative infinity. Ivan. I need us focused. You part of it.
I just took the glasses from I'm helping you out.
Thank you. So, we're approaching that horizontal asymptote.
Come and see what today's announcement.
We are going to play with this and use this tomorrow to help us understand domain and range. Please do not completely pack up unless I have a minute or 2 after they
The
finish.
United States.
I can go down.
I want to